I'm going to discuss the question of turning an aeroplane in a high wind. And the subject is the Earth, the air and the aeroplane, three bodies of mass travelling at different speeds. The Earth we'll consider to be motionless because it is very massive, and any energy created on the Earth's surface does not turn the Earth noticeably, so you can consider it as not moving, even though it is orbiting the Sun at 67,000 miles an hour. So is the air and the aeroplane. So there's no effect from that. So we'll consider the Earth as being motionless, and we'll consider the air as travelling at, shall we say, 100 miles an hour as a headwind to this aeroplane. The aeroplane is travelling with indicated airspeed of 500 miles an hour. That's the speed with which it's going through the air as indicated from the pitot tube, or what other method they use to measure the velocity. Relative to the ground, it's travelling 100 miles an hour more slowly because the wind is taking it backwards. And the ground speed will be about 400 miles an hour. And if you've flown in a commercial airline which has displays on the seat in front of you of what's happening, you can very often be shown the ground speed and the air speed, and you'll see that difference. Over the Atlantic, as I go to Europe every year, I find that as we go there, there's always a tailwind due to the jet stream. This last September was as high as 150 miles an hour, and the plane was therefore travelling 150 miles an hour faster over the ground than it was through the air. And the airspeed is pretty much dictated by the altitude and temperature and regulations and what kind of plane it is, and I think they're usually about 550 knots, but something like that. So I put down 500 miles an hour, and so with a high wind like that, when you're flying against it, you'll have a slower ground speed. When you're flying with it, you get a higher ground speed. And the question that we're addressing is, does that ground speed mean that when you make a turn, your momentum and your kinetic energy have to change if they are measured relative to the ground? And this is how I would normally do that, but I'm sure that many who always speak of the aeroplane as being in the air, not in the ground, that it's flying relative to the air, and therefore it's flying at a constant energy because it's flying at 500 miles an hour, whether it's going towards the same direction as the wind or against it. And when it turns, it will try to maintain that velocity too. So there is that view that there's no danger in turning in a high wind because it doesn't affect you. I say that it does, and the reason is because from a physicist's point of view, the situation is much more complex than it appears to be. The kinetic energy is not the property of a body. Let's be clear on that. A body does not have kinetic energy. And there's two or three reasons for knowing that. Firstly, an airplane like this one has two different kinetic energies, one relative to the air, one relative to the ground. And both the air and the ground are either motionless or traveling at much less speed than the aircraft. So there's definitely a relationship, a kinetic energy relationship between both the air and the Earth. This is often ignored. There's also a kinetic energy relationship with the Sun. And all of these are traveling at some 67,000 miles an hour relative to the Sun, which is an enormous amount of kinetic energy. But they're all traveling together at about that speed, and therefore it doesn't have any effect on us. We don't know that we're moving relative to the Sun, even though we are going round it once every year. So we'll take just these three bodies and ignore the Sun and the Moon and the Mars and Venus and the Mercury and so on. So the Earth is motionless. The air is traveling, and of course it surrounds the Earth, and it travels at different speeds at different places because air is a fluid, and therefore you can't assume that its mass moves in concert all together at the same time. With a solid body, you can treat it as a solid body with a center of mass, and you treat the whole body as moving at one time. But with air, it's not so, because it's a fluid, and sometimes that results in changes in pressure because the air is also compressible. So that if this plane, for example, forces air, shall we say, downwards in order to provide lift to keep it in the air, that air does not continue to travel downwards indefinitely. When an aeroplane flies over you, if you're close underneath it in a smaller plane, you know it, and you avoid that situation. But if you're on the ground and a plane flies over at 40,000 feet, you don't get any draft from it. And the reason for that is that the air, as it goes down, because the air has some mass, although it's small, it compresses rather than being pushed down. And eventually the flow stops, and the energy goes into the compression of the air completely. And that results in the energy being turned into heat. And then heat is, in a fluid, pressure is constant in all directions under steady conditions. And so the temperature involves no kinetic energy relative to anything outside of the air. Kinetic energy within a piece of air that's at high pressure, there's kinetic energy there, but it's all in all directions, and so it doesn't cause any kinetic energy overall for the whole piece of cloud or piece of air. So anyway, the air that's disturbed by the plane is relatively a small proportion of the total air. So the mass of air moved is not very great and does not absorb a great deal of energy. So the aeroplane has energy relative to the Earth and energy relative to the air, and both of these kinetic energies are together at the same time in the plane. It has one kinetic energy for the air, and one for the Earth. Now, can they add together? No, they can't add together because they're not a property of the airplane. They are simply the portion of the energy between the two bodies that is displayed or visible in the airplane, in that it's visibly moving, and therefore you can say it has kinetic energy, but it's not real kinetic energy in the physics term for reality, which is becoming a very popular idea now in physics, that there's what is really going on as opposed to what is apparently going on. Things can be real to us, but not real in physics. So the kinetic energy is very real to us. If something hits you, you know that. But kinetic energy is a property of the relationship between two bodies. So the air to the aircraft to the air kinetic energy and the aircraft to the wind to the air kinetic energy can exist at the same time and have different values. So it has two different kinetic energies. Both energy has a conservation law that says that energy cannot just disappear. It has to be either converted into another form, such as potential energy, or into temperature, heat, or it can be given to another body, but it can't just disappear. And so you cannot say only one of these relationships exists. Both exist at the same time, and both have a kinetic energy conservation protection, so that the energy relative to the air is not of any, doesn't change when the airplane turns, but the energy relative to the ground does. And that's why I say that you have to consider the turning problem as a problem of the kinetic energy and momentum of the airplane relative to the ground, not because it's the only one, but because it's the one that matters. So that when this airplane turns from a for headwind into a tailwind or even into a crosswind. It has to get extra energy in order to maintain the same airspeed. Otherwise it will slow down. And the plane, when you turn in a high wind, you find, well, sorry, in this case it will speed up. It has kinetic energy. No, let me get it right. It will slow down because it has only kinetic energy for 100 miles an hour, for 400 miles an hour. And so when it turns, it can't travel at 500 miles an hour to maintain the flight. It's only traveling at 400 miles an hour. And the plane will not go 500 miles an hour unless you put on extra engine power or make the turn so slowly that